And we start with two talks on forensic DNA. The first is by Roberto Puch-Solis, who's from the UK and works for LGC Limited, which is the laboratory of the government chemist.
Yes.
Yes.
It is.
Okay, there's a different title here. From here, he's going to talk about DNA Lyra 2.0.
Lyra 2.0. Yes. Yes.
Roberto.
Somebody asked me to put a name to the program. I thought the acceleration Lyra was the obvious thing to say, and it stay. Okay, thank you very much for coming. Given all the news, I think many people stay late waiting for the news. I didn't expect to see so many people. I thought you all going to stay in bed because it's raining, physically and also emotionally. Okay, so I work for, you know that in the UK there is no forensic institute like in other countries in Europe, or it's the only country that doesn't have one. So after the forensic science service was closed, the service is provided by, forensic services provided by private companies. There are mainly three companies: Key Forensics, Cellmark, and LGC. I work for LGC. Cellmark and LGC are the two biggest companies. Okay, so this project is, we have many people involved. I'm just doing some of the statistics. We have software developers. We have one person which is dedicated to implement the mathematics. We have a second person, Ricky Young, who designs the graphical interface. And we have a person dedicated to testing. So we have the testing, UI, and the math. We also have the interaction with two of our DNA leads. Tim Clayton, that you saw in the session in September, was here giving a talk, who is our principal scientist in interpretation of DNA. And we have also a principal scientist, which is about technical aspects of DNA. We also were starting a collaboration with Therese to progress the statistical methods. I usually work on my own, so I want some feedback on the statisticians and learn from her and also from you. Okay, can you hear me at the back? Yeah? Okay. If I go, sometimes I just tend to go very low. Just leave your hand and I'll raise my volume. Okay, so we are asked to do this project. It's about statistical evaluation of DNA. So I'm going to show you my requirements, the software architecture, try how to tackle the problem using Bayesian networks. Very briefly talk about gamma models, some results, and the further work that we need to do to complete this project, and some conclusions. So the company now serves a large number of cases, so they want us to develop now that is everywhere. So we want us to develop a system that can deal up to 4-person mixtures, can deal with low-level DNA, multiple profiles. If you have, replicates, when you have uncertainty profiles, it's usually the case in the UK that you produce more than one profile, 2 or 3, mainly 2. Deals with drop-in, drop-out, stutters, and we're going to have we have about 100 users that are going to use the system. Currently, we have about 10,000 cases per year, DNA cases. They are not all the cases end up with the calculation, but a few thousand they do. So you have to have a system that is efficient enough to deal with this load of cases. And they want both likelihood ratios and also mixture deconvolution for different activities. So the software architecture is designed this way. The software is deployed in a web page in our intranet, so only the users who have been through a course and have been signed off to use the system can actually access the web page. we have our own system to produce EPGs. So this web page interacts directly with the EPGs and brings them into the system. Then the user can select all the settings to produce a calculation that can be sent into a set of servers that can chunk the numbers, and then once the calculation is completed, then the server send an email to the user saying, your calculation is ready, please come and collect. So it doesn't block your computer. You can send a calculation from a laptop, and still it goes to the servers. And everything is stored in this calculation database. That also helps us to fulfill our duties to retain the calculations. Also, the system has inbuilt a set of logs in which everything that the user does is logged. So user RPS change this peak from a stutter to an artifact, so it's there. Or RPS, me, Roberto, download this project on this date at this time, and so on. So everything is logged. It can be disclosed to the defense or to anyone who wants to see it. Also, having a web page is very important as version control. So we are in control of the version of the software, and we only release the software once it has been validated thoroughly and it's been UCAS accredited. UCAS is the United Kingdom accreditation system, and the police doesn't accept, in general, any process which is not being through a UCAS accreditation. And here, this is good because some of the managers say, I want a likelihood ratio for 4 people in 10 minutes. Because we have to run our times, our customers are, yeah. Okay, so this is great because then we can throw that question back at them. How much money are you going to give me to buy more computers to put in here? And then they back off, okay. So if you give me money, we'll make it faster. So there is a cost of parallelizing everything, but if they want it faster, they have to invest in more servers.
So how much does a minute cost?
Thousands of pounds. Each server, I don't know, thousands of pounds. So, but it's made it scalable. So, okay. We talk to our practitioners, and we all know that there is with an allele comes an artifact called the stutter, which is one STR less to the allele. I think is commonly known, but now, given the sensitivity of the profiles that are produced, from time to time we see small peaks which are 2 STR less to the allele. So we need to change our name and not talk only about stutter, we talk about back stutters and double back stutters. And so it was actually a requirement by the practitioners because they spend a long time discussing with other people and with defense experts what are these little peaks in your profile and why you have designated as an artifact. Sometimes they are the same height as drop-in, and then there's an endless discussion about what these little things are, which perhaps don't matter much, but it takes a lot of effort to discuss and to talk about them. Then we have also forward stutters, which appears in more or less at the same height as the backward stutter. There are other artifacts. These are not all the artifacts. Locus SE33 has other artifacts which are not modeled. They have some peaks that appear two base pairs less than the allele, and there are also other artifacts appear here and there. So it's not everything, but we can do as much as we can to have a consistent and efficient way to deal with these things. If we define back stutter proportion as the proportion of the allele that goes to the stutter in comparison to all of these peaks, in D3, this is kind of what you can see. The proportion that goes to the double back stutter is of this order, which is similar to what it goes to the forward stutter, and here is what we know usually happens with the stutter. In the European set, there is a locus D22, who is a trimeric locus. Instead of having 4 repeats, it has 3 repeats. So you have 3 base pair repeats instead of having a 4 base pair repeats. And it's known that these locus tend to stutter more. And when you look at the numbers in here, you can see that the back stutter is about the same order. These as well, but if you can see here, the forward stutter is significantly larger, almost as large as the back stutter. These and these, sorry, this and these are kind of similar. This creates a problem when you have 2 alleles which are non-adjacent with one space in between. Then you can see that the back stutter of this guy combines with the forward stutter to this guy to create a peak which is larger than the usual artifact. This has to be considered in the model. And here you can see almost, it's a good picture. As you can see, the forward stutter is kind of for some reason, this picture is almost, when the profile was produced, it went to the mean value of this stutter. So it's a good picture. You can see that the post stutter is slightly lower than the back stutter, and you can see the combination of these two to create problems.
So this is all done on known samples?
This is non-sample. This is one of my colleagues. I have to ask him, can I use the profile? Yes, sign here. So the main task to calculate likelihood ratios is to assign a probability density to a stain profile given putative genotypes and some parameters, the mean proportion and other parameters. The other component are just 2 main components. One is the probability density of the stain profile, and the other component is the genotype probability. The calculation of genotype probabilities is non-controversial, since it's been established. However, there are many versions to it. There are different ways to do so. There are different corrections, there are sampling corrections, there are co-ancestry or breeding corrections that can be used in different ways, and so on. But, so it's another discussion. We focus on this probability. Once you have the 2 things together, it's like playing Lego. You can put together all of these probabilities to form likelihood ratios or to form mixture deconvolution tables. Okay. So using a gamma model, what we do is to assign gamma distributions to peaks. And then once we have that, we can compute the probability densities. And if there is dropout, we compute the probability that the peak is under a threshold or an analytical threshold. And then we multiply across all these probability densities and the probabilities of dropout to form an overall probability of the stain profile. This is what happened. So recently, the authors which are in the audience have published this paper about the use of Bayesian networks to calculate likelihood ratios. They have this paper, and also there's a paper with Robert Cowell and Julia Mortera, who's also in the audience. So if I say something wrong about your research, please correct me. But yeah, the idea is how can we use this technology to deal with all the stutters, and what are the problems? I find 2 issues. I went and tried to see what happened. There are 2 issues. One is number of parameters, and the second issue is the size of the conditional probability tables in the Bayesian network. They are too large. So the way that this works, we have a section that models the genotype probabilities. So these numbers are 0, 1, and 2. That tells each of these lines is for 1 allele. And this tells me the contribution of allele 1 to the peak height in here. It can be 0 contribution or 1 contribution for a heterozygote or 2 for a homozygote, and so on. So in here we have the genotype probabilities for a second contributor, and in the middle these variables model the peak heights they are binary variables, 0, 1, that, indicating whether a peak has been detected or not, but also considers the likelihoods of the peaks that you observe that can be added to the overall calculation. So, and in doing this factorization, you can speed up the calculations instead of listing all the genotypes, which is the usual way to deal with this problem. You factorize the genotypes in this way, and then you can do it much faster. Perhaps up to 8 unknowns has been done. 6. Okay. 8, sorry?
8 contributors, but 6 unknowns.
6 unknowns. Okay, 6 unknowns, which is
know as many known as you like.
okay. So it's faster than the usual. So it was worth it to have a look and see how we can use this methodology to put more complexity and deal with the stutters. So if we look at this part for a moment. So each of these is for one contributor. So if this represents the peak height, we have the contribution of the allele, and we have the contribution of this back stutter of the next allele. And for contributor 1, for contributor 2, for contributor 3. And then this is an indicator variable. So the overall, we have 6 nodes with 3 levels plus the middle one, which gives me a table of 1,000 probabilities. So it's good you can do that, and then they can do that and very fast. So interestingly, when you look at this, it's almost the reverse way. You should think of stutter here, but then the stutter comes from the guy in here. Switch around. Took me some time to visualize it well. It's the other way around. Okay, so when we want to do stutters, then we have the contribution of the allele, the back stutter, the double back stutter, and the forward stutter, and then we have this for all the 3 contributors, and then what happens is that the table grows significantly because we have about the table associated to this node is 500,000 probabilities, which, well, a computer can deal with this, but when you want to construct a junction tree, then you have many nodes which have 1,000,000 entries, and then the computer says no, which makes sense. So mainly because I was using a library called grain, which has a pre-constructed algorithms for Bayesian networks, and they didn't have access to tweak the algorithms to start looking at different ways we can do that. I tried to do so, but then it was not possible to actually access the different algorithms that build a whole propagation algorithm. It is possible to do, but I ran out of time, so we're talking to Therese on how we're going to can approach this problem and how can this be solved. And we know that Hugging has this compression tables feature that can reduce the size, but there may be other ways to do so, maybe by dividing the task into smaller parts. We are talking about size against time, calculation time, and how we can find a trade-off to do so. But the main problem is that to do so, you have to have your own algorithms to start tweaking everything as you need to. And I didn't have that, and I don't have the time to go and program everything. So I needed to go back. Unfortunately, I was very excited to do so, but after some time fighting with Grain, I went back to the standard method to list genotypes. But this is a nice area that we need to go back and look at. The another thing that I was looking at is that in this program, they have parameters that are optimized across the stain profiles, mainly the stutter proportion for the back stutter and the scale parameter for the gamma distributions, where you can define the shape parameter and so on. To extend the methodology, we have to start looking at not only one parameter for the back stutter, which I call the psi of -1. Also, we have to look at the parameter for the forward stutter and a parameter for double back stutter. And also, we know that, as we see, D22 is a very different locus where these proportions are different. So it's a locus that we know that these proportions tend to be much, much smaller. So there are differences between loci. So we need to look at many, many more parameters. And then I was looking at the scale parameters, and the scale parameters can be different for the different loci. But then when I start attempt to estimate the scale parameters, I start realizing that perhaps the scale parameter is not the same for all. So this is some other area that we have to look more in detail, which create a problem because we cannot adopt gamma distributions that do not have the same scale parameter. So what do? Close my quit and say, well, I can't do this. Or do something approximate. It's too far now. So what I'm going to do then is I want to estimate these parameters. I can only then combine gamma distributions by maintaining the means and the variances, but which is not such a bad, shouldn't be such a problem because the most dominant gamma distribution is that of the allele. So when you have smaller gamma distributions contributing to it, it shouldn't create a tremendous perturbation. So it's approximately right, but it requires more thought. I mean, DNA mixtures works well, like LTD also use the same scale parameter, it works well. So there is an idea that there is not such a great impact on this aspect. So we have 112 parameters that we can estimate from an stain profile. So what we can do, we can look at profiles of no origin, the so-called dilution series in which we create DNA from the lab and then divide it in small pods and then create profiles at different levels from which we can estimate the parameters. And so I did so, and this is a back stutter for D3. I use the sum of peak heights as a DNA proxy, and I can estimate the mean of this gamma regression and then the scale parameter for it. And it seems to represent well the variability for which we can take the gamma distributions that we require to work with. We run a profile, and it seems to be that the target mixing proportion was 0.8, 0.2, and the estimated one was very similar. So it seems to be that if you consider one gamma distribution, then it can generally work. But another thing, when we see the deconvolution tables, we can see that out of the 16 loci, 11 loci, the first genotype was the correct one. In 4 loci, it was in the second position, and in 1 locus, it was in the third position, which is what you expect to see. You don't see the correct genotype being at the top of the list all the time. We have done a mixed deconvolution model in the FSS back in 2011, and we have this variability. Mostly, about 70% of the time, you get the correct genotype at the top, but you do get the correct genotype at lower levels as well, lower in the list. But we have a problem because if you look at our data, you can see that if you see allele 16 at this locus, allele 16 it produced this mesh of data, while allele 25 it produced higher stutters. So that suggests that there is a dependency of allele numbered stutters, and whether actually is it right to use one gamma distribution for all of it, or we should use one gamma distribution for each allele, and how we can achieve that. Well, this is not new. Sorry. First, if you plot here the back stutter proportion against the allele, then you can see that there is some kind of a structure here. There are 2 lines in here that you can infer. So obviously there is there's dependence on the allele number, but not necessarily on the magnitude of the allele or number of STRs. So this is not new. It comes from research from Brooks et al. Back, it was in the ESR. I think James has been involved in this. You have a big question, James can answer it. So he has published several articles in this matter. Also, and the use of this longest uninterrupted sequence for double back stutters and YSTR profiles. And there have been a number of papers on this topic. So if you use the length of the longest uninterrupted sequence in the motif of the DNA, then you can see that this aligns better. So there is something about the size of the uninterrupted sequences have an effect on the degree of stuttering.
Well, what is an uninterrupted sequence?
I'll tell you now. So when you see alleles, for example, allele 17, if you see the actual motif, you can this notation says that there are 4 repeats of TGCC and there are 13 repeats of TTCC. So these guys are the longest. This guy is the longest uninterrupted sequence. They have a 13 LUS. The length of the LUS is 13. There are other versions in here. You see in 20 we have all these versions. 23 we have all these versions. So you don't have one. Now that NGS has become more possible or is accessible, then we start having more information about the motif of the alleles that we can use to do stutter modeling. And you can see that it's a large variety. I showed this to my molecular biology colleagues, and they were very excited to see that there is one population here where this sequence was interrupted by one mutation. This T mutated to G and interrupted this sequence. And then you can see as well in here that there was another mutation from this C to this T, which interrupted as well this sequence. So they see that this is a population with some variants, and these 3 guys forming 3 separate populations of alleles.
So this is interesting. I always assumed that the allele of the repeat number was a repeat of a single sequence, but it isn't, is it?
No.
Lots of repeats of different sequences.
Yes.
And there's a lot more structure there than we think there is.
There's something there.
Yeah. It makes you scratch your head very heavily.
Bill Johnson is rubbing his hand.
Yeah. So nowadays we have gettings. We have STR base before. Now we have gettings and all to have produced some data that we can use to look at the structure of the motifs to do more modeling. But there are questions regarding how you're going to use this information, because you have choices on how you allocate your choices, how you apply your model. Even if you have a model that takes into consideration these numbers, which one are you going to use? You have many. So so perhaps we can then, if we have a model of these kinds in which we can model the LUS number against to predict the stutter proportion, then you can have a model per allele. D3 allele 15 has his gamma distributions. And in here you can see that we can estimate the scale parameter, the same for all the alleles in the locus, and do this type of modeling. And also notice that here, obviously, at low levels, there is more variation, and therefore, when you do your gamma regression, then it needs to be a compensation for more dispersion at the low levels. So you need to do a weighted gamma regression. And you can see this more in the 99% probability interval, in which there's more variability assigned at these levels than at these levels. So if we saw that we can have more than one motif for one allele, so how we can actually use this information to calculate probability densities for a peak. So
can I just check on what you actually normally measure? So if you've got 2 different motifs that contribute, and that you would just throw it all together, I mean, would you normally be able to, in standard case work, can you separate out the individual motifs?
not at the moment, no.
You can't. That's why you said.
Yes. So you don't know.
So the data you showed us earlier, what was the source of?
It's the data that I have, but
with the different patterns and what's included.
This sequencing is coming in, but it's not there
So
yet,
this
but
is-
it will
this
be
is-
soon.
this
And there's
is
plenty
the
of
future.
development work on sequencing.
yes.
This is the future.
Yes.
And so,
The near future.
so in future you're going to be able to distinguish all those 3 different ways of making up an allele 17.
Yes. And then we will have frequencies associated to these alleles,
Yeah.
so we have more variety, more discrimination. But it's not yet there, it's getting there. There is more lot of work going on.
New databases.
New databases, new models. It's exciting. I need to do something different, bigger. So, but in the meantime, how can I assign a stutter proportion if I'm not sure which one is which? Well, the only thing that can occur to me is to use a mixture of gamma distributions. So we have a gamma distribution for one motif. If you would have two motifs, then you would have a gamma distribution for motif 1, a gamma distribution for motif 2, and then you will have a mixing probability to be able to apply the model so you can add up the contribution of an stutter with an allele and so on. The question is then, where do you get this piece? Thankfully, there is some studies coming on in which these pieces are being estimated and we can use. So this perhaps as much as I can say now. This work is going to be published soon, from where we can potentially take these numbers. Okay, so I promised to finish half, but there's another model that takes into consideration drop-in. But perhaps the main part of my talk was to talk about the stutters and the motifs and all of this. But the main issue is that once you have a peak that you need to explain as a drop-in, if the p-value donor is 1011, then you have there are a set of factors that you multiply the probability density of the profile that consider the incidence of drop-in and the probability that the allele 13 will drop in, and also there is a probability density on the drop-in height that can tell you if you are proposing a peak height which is drop-in and is not in the predicted interval of this gamma distribution, is going to reduce the likelihood ratio by a lot. And the peak heights of drop-in does follow a gamma distribution more than I thought. I need to check this several times because it's too nice to be true. But it does happen. And all this data is being produced using extraction negative. So basically you put everything except DNA, and you should expect not to get anything. But from time to time you get peaks that you should be getting, which is just fragment of DNA that comes into the process, maybe during the manufacture of the process, maybe there's a bit of DNA floating in the air that can fall. If you have Peter Gill here, they can tell you all the stories about this. What's your term? No, you just introduce the term drop-in. I think so. Yes, you can measure this. There is not the only way that you can model drop-in, but this is one way to at least account for it. Okay. So we are going to implement this model once we have all the information. We maintain the uncertain peak that is in like LTD. In like LTD, the discrete version of like LTD, there was an uncertain peak that was either there or not. So we have extrapolated and maintained an uncertain peak and then consider different levels of this peak, because sometimes, very rarely, for example, pull-up can affect a peak in an allelic position. And then there's a way that you can deal with these very rare artifacts. We need to we will do an extensive validation using hundreds of mixtures of origin. As you can see, it's not really new. It's taken research from what one group does, and taking research for what Therese is doing, what Stefan is doing, what David is doing, what James is doing. Different people are putting together in the model. We put together a paper and to explain how all this works. And so I have 5 minutes more. Thank you for your attention.
Thank you very much, Roberto. And we have time for discussion. Start here.
Do you concentrate your model several different number of contributors?
Mm-hmm.
Because I suppose that a priori you don't know how many contributors in this DNA mixture there are.
Yeah.
And if you do, then I suppose I fail to see that of course, with more contributors, you can explain better your data, so your likelihood drops out. It's lower. It's compensated by what's called the open factor in a Bayesian framework, which is the priors for the extra parameters that you have to put to model that. I don't know if you consider that.
Yes, we have a very interesting discussion yesterday about this issue that was brought forward by William Thompson in the example that he produced. Also, some good ideas from David Boulding and others. The main issue about all this is that it takes time to compute, and the reason why we are not computing for any number of contributors is because we don't have. It takes time to calculate. But what we should do, it's clear in my mind now, and I hope that if you agree with me, is that we can assign a prior to the number of contributors and then compute all of the likelihoods. So we deal with the number of contributors as a nuisance parameter in a Bayesian way. It's about, in the picture of the system, it's about putting more computers at the back so you can do this regularly. And you don't have the same number of contributors.
Yeah, I was just wondering, it might be a silly idea, but in your representation with back stutter, 2 back stutter, and 1 forward stutter, instead of making that one big clique, maybe one could get the stutter contributions on one of the O nodes of where you put your likelihood and break them up into single combinations. I mean, for example, I don't know, take the 2 back stutter with the back stutter, make back and 2 back stutter. Well,
okay, so we have like a
sort of break it down. It's called divorcing in.
Okay.
In I don't know if that might be a good idea. Stefan would know.
I was going to say the same thing.
Okay.
The point is that in Bayesian network sort of technology, the real bad thing, the thing that kills everything, is a node with many parents.
Yes.
And this is what you have. And this is always what. And the standard way of doing that is simply to introduce more nodes that do the intermediate calculation. If you, for example, if you have a node that is the sum of 10 things, right? You just add it like it's one plus the other plus the sum plus another one plus the sum plus another one. So, and you can do that in a. I don't know whether you can do that here, but I think you probably could reduce the complexity quite drastically, because this is a very bad representation.
Yes.
And generally, the philosophy behind these Bayesian network technology is that don't use your mind. And don't do formulas. Don't reduce things by making formulas that look simple to you, because they don't look simple to the computer. So rather break the network up into little items that each have simple relations with each other, and let the computer do the calculations. And that's usually what can speed up efficiency a lot. I don't know whether it will solve this problem.
Yes.
But because this is not so easy just to see. But generally, one has to put that into one's mind, that this idea of making a simple reduction and a simple formula is good for me, but it's not good for this
Calculation.
CPU thing.
Yes. Point taken.
We've actually published a paper using a technique called binary factorization. We exploit the commutability of arithmetical statements as a form of binary factorization as a form of divorcing. And we have a special set of algorithms that can exploit that for inference purposes, which extend junction tree. It can also be used on more advanced algorithms like region graphs for approximation, for continuous inference and Bayesian nets. So it can take you to new places, whether it's applicable for your large exploding cluster. I'm not sure. Maybe we should talk about it offline.
Yes, if I can have the paper and have a look and see whether we can divorce the graph.
I mean, you can think of something like multiplication is just a little Bayesian network with 2 parents, which are the factors, and one child, which is the product. And similar with all the other elementary operations.
But I can see how can I put a different contribution in one node, and then to put one big node to contribute to one allele. And then we'll reduce the number of parents. Sorry?
Okay.
But it doesn't always work.
Yes. Yeah, there was a question.
So your model of drop-in towards the distribution was very interesting. I don't think I've seen that before. It must be hugely dependent on all kinds of factors. I mean, it must be lab specific, and
Very lab
but also, do you have any kind of data on that? I guess you don't about the variation there is across labs.
What we do in the lab, because we produce many profiles all the time, so it's a standard to put extraction negatives in the plate. So we do have this data on a routine basis. So this data is then produced to check whether contamination is there or the levels of drop-in are increasing or decreasing, so you can make decisions regarding.
Okay, but even perhaps more importantly, these are lab negatives,
Yes.
right? And so there's always been this slight confusion in my mind about what drop-in means for a crime sample, because I think many people use it for only lab origin, generally airborne fragments, I think is thought. But it seems to me that that's kind of useless in practice, because there can be trace level DNA contamination at the crime scene. You have to distinguish that from lab-based. So it's going to vary from crime scene to crime scene.
Yes.
Sorry, Dave, that's irrelevant. The contamination at the crime scene, obviously you can't control for. The drop-in parameter is solely a laboratory-based parameter. If you have contamination at the crime scene, what you end up with is a gross contamination, then it's just a mixture, and you just analyse it like any other mixture.
No, but I'm talking about the same kind of airborne fragments or whatever, the tiny traces that are there in the environment outside the lab as well as inside the lab, and you can't distinguish them in your modelling.
No, you can't. But you cannot measure the drop-in that occurs outside the lab. What I can do is to measure what I can measure and account for it.
But if you were using that as some kind of prior, is that what you're doing?
Yes.
Yes. Then that won't capture any similar, fragmentary DNA that's come into the sample from the crime scene, and that might vary from crime scene to crime scene.
Yeah, it may. Yeah.
It's pretty insensitive, though, isn't it? Look, do you agree, Roberto? Because we've modelled this parameter quite a lot, and it actually makes very, very little difference to the likelihood ratio.
Adding a drop-in correction have a tremendous impact on.
Most strikers on
Bill?
Did I understand you to say that the drop-in probabilities may be dependent on allele?
Depend on the size of the allele, but usually you cannot model that because it's a rare event. But it depends on many things.
Yeah.
It primarily depends on the system that you use to produce profiles.
Do you have any theories as to why that might be, and what and what is the relationship? I mean, the smaller fragments are more likely to drop in, or less likely.
You all tend to see drop-in more in the low side, which is the lower molecular weight and the high molecular weight.
Okay.
You tend to do that, yes.
Okay, and then the theory is that those are more likely to be, are more easily transferred because they have a smaller mass?
Yeah, when it's detectable, it's just if you think that there is smaller, more frank, there are issues that the DNA degrades, and the smaller fractals are degrading, and some of them they degrade to a way that they cannot be amplified, or there are not sufficient amplification to detect, while the smaller fragments are more likely to.
Okay.
Because I don't understand. I take that from my biologist friends. You can see Peter here. That perhaps the theory is that you have DNA, and when it degrades, it cuts the DNA to bits.
Yeah, we use the snowing from the ceiling analogy. So what drop-in is, we think it's a highly fragmented DNA. So they're not complete genomes, they're fragmented genomes. For example, house dust contains human DNA, for example, but it tends to be highly degraded, which is why when you get a drop-in event, it tends to be low molecular weight rather than high molecular weight, and you get the end up with the graph that Roberto showed.
Okay, thank you.
Yeah, we have just more discussion at coffee. I think we must go on to the next talk now. Thank you very much.